All right. Okay, thanks for coming. So today we're pleased to have Eng Keat, who will give his first talk in Korea, or in I guess, which one is correct?
Yeah.
All right. We'll talk about branching process. Please.
So thanks Sang-il for the introduction. So as Sang-il said, it's my first talk here at IBS. And since I joined EcoGrow, so my talk today will not really be about extremal combinatorics, but a lot more about the probability side of things. And in particular, I will talk about Graphon branching processes and how these relate to a notion in graph theory known as fractional isomorphism. And so this is based on joint work with Jan Patki and Anna Limbach, who are both at the Institute of Computer Science of the Czech Academy of Sciences in Prague, Czech Republic. So just to begin, let me give you a quick overview of my talk today. I will start by talking about the Erdős-Renyi random graph and a classical result about its component structure. And to better understand this, we will look at an algorithm for component exploration and how this relates to a family of random processes known as Galton-Watson branching processes. And so moving on from that, I will talk about separately a different model of random graphs, which were introduced by Bollobás, Janson and Riordan almost 20 years ago now, which are parameterized by something called a graphon, W, which is a type of dense graph limit. Again, I'll talk about its component structure, how you can do all these explorations, and some natural branching processes that arise from that. And so this is where we will see one of the first of our results, which is a sort of characterization of these branching processes in terms of a classical notion, a notion derived from something in graph theory known as fractional isomorphism. And if time permits, we will see a bit more about a different random model known as uniform spanning trees. And we have here our second result, which again gives a characterization via fractional isomorphism for these uniform spanning trees. Right, so to begin, let me talk a bit about the Erdős-Renyi random graph. So as some of you may know, the Erdős-Renyi random graph, GNP, is a random graph on n vertices, usually 1 through n. And what you do is you have each pair of vertices ij be an edge with probability p, independent of all other pairs of vertices. So the Erdős-Renyi random graph is something that features in many parts of combinatorics and graph theory. For example, it's often used as a tool by the probabilistic method to prove results in extremal graph theory and Ramsey theory. And it's also sort of studied for its sort of as an object on its own in the sort of well-developed theory of random graphs, of which it is perhaps the first random graph to be studied. And so to date, we know a lot about the Erdős-Renyi random graph. We have studied many graph properties. Some include connectedness, continuum of subgraphs, homotonicity, and so on. And often what we study when we consider these properties is that we look in the so-called asymptotic setting in the sparse regime, meaning that we care about what happens as n goes to infinity. And we often don't look at a fixed probability p, but rather some sort of probability function pn. And typically this will often go to 0 as n goes to infinity. And many results in this area have the form of sort of a threshold function for the emergence of these properties. And often you see these so-called phase transitions, where sort of you have what is called a threshold function, below which you don't see the property, in some sense above which you always see the property, and sort of crossing this threshold at varying speeds, depending on the property you're looking at, you'll see this sort of perhaps sudden emergence of the property. And so from this sort of one very classical result about the Erdős-Renyi random graph is the so-called emergence of the giant component in the Erdős-Renyi random graph at the probability threshold of 1 over n. Oh, that was a mistake. Oh. 1 over n. This is sometimes known as the phase transition in GNP because of how sort of well known it is. And this result dates back basically all the way to when Erdős-Renyi and Renyi started considering the random graph. And it concerns the size of the largest connected component in the arbitrary random graph, and goes as follows. So for the purpose of this statement, I will just focus on probabilities around the threshold of 1 over n. So if we were to look at the arbitrary random graph at this range of probability, where p is equal to lambda over n for some lambda real number, positive real number lambda, and n going to infinity, then what it says is that the size of the largest connected component, when we are below this threshold, so delta, lambda less than 1, we have components whose sizes are all of fairly small sizes, in particular always of order logarithmic in n. But sort of as soon as you creep above this threshold of 1 over n, so meaning lambda greater than 1, then this largest connected component suddenly becomes of linear order. So it sort of explodes. Hence the name, the giant component in this GNP. And in fact, we can write a function for this order of the largest component, which we'll come back to see, we'll see a bit later as well. Right, so now let me sort of, to motivate the rest of this talk, let me talk a bit about how some of these proofs went. So much of the early work on the arbitrary random graph and the component structure were enumerative, meaning that you sort of had to do a lot of very detailed calculations, and once you do them, then you will find something that tells you that this is the right answer. But sort of when Karp was investigating a different but highly related problem in 1990, he sort of gave a different idea as to how one could actually approach such problems. In particular, he used the idea of sort of the exploration of these components with an algorithm, and sort of analyzing this exploration via a bunch of random processes known as Galton-Watson branching processes. And so before I get to this algorithm, let me first say a bit about these Galton-Watson branching processes. So Galton-Watson branching processes are a fairly broad and general family of random processes, the study of which was originally motivated. If anyone has any comments to add, please feel free. Where was I? Right, so the study of this was originally motivated by Galton's great interest in the survival of family names. So, for example, in Korea, whether the Kim surname will eventually die out or something. And so, for this reason, he studied these things together with Watson. And so, for the purpose of today, I will focus on what is sort of the Poisson case of this. So we will, in particular, the Poisson distribution will come out somewhere. But anyway, let me give you a definition for the processes that we will care about for today. So we write GW lambda for a branching process which goes as follows. So in sort of the original generation 0, we have a single vertex. And the main thing we need to specify when we define branching processes is how do you sort of branch out from each vertex. And so, okay, so for the purpose of today, we will look at a sort of Poisson branching. So Poisson meaning a distribution on the non-negative integers given by a probability mass function as follows. And what happens is that in each generation, and for each vertex, you have Poisson lambda many children. So maybe one thing to know about the Poisson distribution is that this parameter lambda is sort of the expected number of children that you would have. And okay, so then what you don't define is sort of the next generation is simply the children of the current generation. So to give you an illustrative example, in case this bunch of words was a bit too opaque, let's suppose I have lambda equals to 2, so meaning my Poisson distribution expects to have 2 children on average. I will start with one vertex in generation 0. And so now what I need to do is basically generate the children. So this will have Poisson 2 children. Maybe I will, run some simulation, find that this will get 2 children. And since this is the only vertex in generation 0, these form generation 1. And now for each of these two vertices, I will now need to generate yet more children. So for each of them, they will have Poisson 2 children independently of each other. Maybe this one, the first one has 3, the second one has just 1, and so on and so forth. So I'll generate another generation, you get maybe this many. And okay, I can't really draw the rest of the thing because it's supposed to go potentially infinitely. But sort of the thing sort of going back to what Galton was interested in, the survival of family names, what one often looks at is sort of the survival of the branching process. So meaning whether this branching process will branch off sort of infinitely. So we say that it survives if every generation has at least one vertex, or whether it dies out at some point. Because, sort of recall, because we have this Poisson distribution, the probability of it being 0, for k equals 0 here, is rather non-negligible all the time. And one key property of this process, which will come back to matter in this Schwenny random graph, giant component thing, is sort of, we know that the survival probabilities, we can understand a little bit about them. So in particular, if sort of this lambda is at most 1, then the probability of this branching process surviving is always 0, because you can sort of imagine if you have, on average, at most 1 child, then things might sort of slowly die out, and eventually every branch dies out. Whereas if you are above 1 with this lambda, then you have a positive chance of actually surviving, in particular because you may have more than one child every generation. Right, so this is all for the Galton-Watson branching process. So coming back to this whole thing about exploring the Schwenny random graph, so the algorithm that one uses to run this exploration is as follows, and sort of for people who might be familiar with such terminology, it's basically a breadth-first search algorithm. And so what you do is you start with one active vertex, everything else inactive. And basically, you want to explore the neighborhood of each vertex, each active vertex. So you pick an active vertex and simply test what does its neighborhood look like. So in particular, you test whether there are edges to every other inactive vertex. And sort of you activate those vertices that you can reach by an edge, and otherwise you don't activate the vertex. And once you're done with this, you mark the vertex that you were studying as explored, and you sort of repeat this process. And you stop once you run out of active vertices. So again, to give you an example, suppose I were in Gn2n for some large n, maybe n is 100, because why not? And I start from some vertex, maybe vertex 1, because again, why not? There's no real reason to prefer 1 or 100. And so what I'll do is I will look at all other vertices, which I have now marked here in these little black dots. And I'll see, okay, well, whether there's an edge to each and every one of these, what does my neighborhood look like? And maybe, okay, since the probability is sort of fairly low, it's just 2 over n, where n is potentially very large. So on average, I pick out maybe something close to 2 of them, maybe, in fact, exactly 2 of them. Maybe turns out to be these two fairly random numbers, 25 and 74. And sort of, okay, we just iteratively do this. Now I start from 25 instead. I will have all the rest of these vertices, which are inactive. I check whether each and every one of these has an edge to 25. So, and okay, I do this also for 74, and so on. Right. So the thing that sort of we need to note here is that given how we were exploring these neighborhoods, these components, via this algorithm, what sort of happens in each step is that we are sort of testing for, let's say, vertex 1, for example, initially, whether there were edges to 99 other vertices, or more specifically, more generally, n minus 1 of them. And since we're in G and P for P of this form, we have this sort of probability like this. And sort of the key thing to note is sort of that as long as C is not too large, then actually this random variable here is roughly like a Poisson distribution, which And so in some sense, one can say that as long as the exploration process doesn't go too far and see too many vertices, this looks kind of like Galton-Watson with parameter lambda or 2 in this example.
So we do not revisit the already explored vertices, right?
Right. So once we see them, we activate them, and we don't actually ever test against other active vertices.
And this this approximation is only for the maybe the initials. This is n minus c is very large, right? Only
Right. So I'm not really being extremely precise here, but sort of that's sort of the heuristics behind this. And sort of, right, so why is this sort of relevant? Because, right, so in particular, since we have this, okay, so exploration behaves like this, and sort of recall we had this whole thing about the survival probability, so again, sort of using some heuristics without being actually precise, you can sort of think of the process dying out as somehow being in a small component and not really seeing anything large, whereas if you were in something big, then you could, in theory, explore forever. Of course, you might ask the question, or you might complain that things will, of course, at some point break down because you start seeing too much, but sort of the thing that happens here is sort of, in the theory, if you do everything rigorously, you can sort all these things out. And sort of what this gives you is that the giant is roughly of the following order, so n times the survival probability of this random Galton-Watson branching process. Right. And so in some fairly hand-wavy sense, we have proved that this happens, that this Galton-Watson branching process is really somehow what is driving what's going on in the Erdős-Rényi random graph in terms of its component structure. All right, so next I will now talk about a different model. So before I introduce that model, let me give you an introduction to this beautiful and wonderful theory of graphons. So to begin this introduction, let me give you an example, a definition. So a graphon for us here will simply be a symmetric measurable function on the unit square, taking values in the unit interval. Some of you may have heard this phrase before. And one way to think about this okay, so right. So what I mean by symmetric? So by symmetric, I simply mean that the two parameters sort of because I'm on the unit square here. This sort of the function is symmetric in the sense that if for all x and y in 0, 1, wxy is equal to wyx. So, right, and sort of the intuition behind a graphon here is somehow you want to sort of represent what happens if you were to take large graphs and look at their adjacency matrices. So more specifically, let us see roughly how we can get from graphs to graphons. So the first step you might do is you might want to represent each finite graph via its adjacency matrix. So take your favorite graph, maybe it's very big, maybe it's very small. I am not very ambitious, so I'll pick only this very small one over here called C5. And what I'll do is I'll write down its adjacency matrix, and then so here this is an array, but now I'll put it on the unit square, choosing a slightly weird orientation of the origin, with the origin being here and 1, 1 being here. Then I will simply cut it up into this 5 by 5 grid of little squares, and we will see a 1, which is represented by this sort of black square, and a 0 whenever which is represented by this white square over here. And sort of the way that we get to graphons is that instead of looking at just a single graph, we will look at graph sequences, and we will take a limit of these graph sequences in some sense, which I will really get into because it's a bit technical. But sort of giving the following example, where we have a sequence of graphs of the following form. So a clique in black, an independent set in white, and sort of a bipartite graph of some density between 0 and 1, let's say a half, going in between, and somehow the edges are distributed randomly. Then, if we were to take a limit, the sort of natural limit for this, which is the graphon, is the following graphon, where you have this square of all ones representing the clique, all zeros representing the independent set, and this random bipartite graph here represented by these two rectangles of the value of half on them. Right, so if all these graphon things get a bit complicated, just think of a very, very large adjacency, an adjacency matrix for a very, very large graph, where you somehow have smudged all the zeros and ones because you were a bit too careless in how you were writing them down. Okay, so slightly annoyingly first, I didn't actually want to say this, but we will need to actually work with a slightly different definition for today, which is that of a kernel instead of a graphon, where we, instead of taking values in the interval 0, 1, I will take values in a non-negative real. So this is a bit of a technical thing just because we will have to divide by some large value, and yeah. Alright, so now moving on, I will now introduce to you this model of inhomogeneous random graphs, which were introduced by Bollobás, Janson and Riordan some almost 20 years ago now. So this was in a fairly big and impactful paper of theirs. So this paper took up, was like 100 pages, taking up a whole volume of an issue in, no, a whole issue of RSA, issue of volume, anyway. And basically the only other writing in this volume was just that this is amazing. This extends Erdős-Renyi random graphs. Right, so what's the definition? So it in some sense extends Erdős-Renyi random graphs. So okay, again we have vertices 1 to n. But sort of because we are working with this kernel, we need to randomize things a little bit. So in addition to having these vertices, we need to pick uniformly at random endpoints, x1 to xn, in the unit interval independently, sort of to represent where these vertices are. And now for each edge, instead of a fixed probability p, we now have a pair ij be an edge with a probability given by this following expression, wxi xj divided by n. Right, so just to give you a picture as to how this might look like.
Are you sure that W is at most n?
So okay, I'm being a bit careless here. So, right, so
you said it.
Yeah, so of course, to be more precise, one will need to take a minimum of this and 1, and maybe you have a kernel which is bounded by some value and so on. But sort of modulo all these little technical edge cases, this is basically what you do. And often n is fairly big, so the sort of places where this isn't quite correct is not very significant. Right, and okay, so to give you an example, let's suppose I have the following kernel W, again with my slightly funny orientation, with the origin being in this corner. So I have vertices 1 through n, let's say in my graph, so 1, 2, 3, 4, and everything will disappear until n. Then, okay, so what I'll do is I'll randomly sample these points, x1 to xn. So let's say in particular, I was extremely fortunate in somehow getting x1, x2, x3, and x4 to be so evenly distributed. And now I want to put the edge, let's say 1, 3. I'm interested in this. So what I need to do is I need to go into this kernel, look at x1, it's here, and sort of look at the other axis to find x3, and sort of now take the value at this point, which is precisely this wx1, x3, and then divide it by whatever n was. And then flip this coin that's extremely biased. Right, does that, yes?
So we assume there is no loop.
Right, so this is a bit of a, yeah, so we don't do loops, so for I not equal to j all the time. You could do it for loops, but this is a different theory somehow. And you can always, of course, one thing is you might notice that like you can, in theory, put a diagonal of all zeros on this sort of main diagonal, and okay, you're getting a bit into the technical details, but like there's this thing in Graphon theory where like changing things on a measure zero set doesn't really matter. So you can make all these little changes. But yeah, we usually do it without loops. Okay, so so again, we would like to understand the component structure in this slightly more complicated random graph. And sort of the idea here is sort of to look back at what Karp said before, so we can understand the structure in Gn lambda over n, where lambda over n is some constant, by looking at what happens with this Galton-Watson branching process delta. And so the natural thing to expect or hope for, and what Bollobás, Janson and Riordan essentially prove, so this is a bit of a meta statement, that we can understand this inhomogeneous random graph by understanding this analogous Galton-Watson, inhomogeneous Galton-Watson branching process. And so you might realize that I haven't actually defined for you what this funny process is. So let me now give you a definition of what this process is. So, alright, so as before, we start with so we have this kernel W, which I have drawn over here. And we have a starting vertex, as we had before, with the Galton-Watson branching. But sort of the main complication that arises working with a kernel, where things are a bit less clear-cut, is that you kind of need to care about, so sort of recall we did this thing with the sampling of a random xi for each vertex. So things get a bit more complicated in the sense, in that you need to sort of decide what sort of vertex this is. Right? So is it a vertex that lives here and sees, in some sense, neighbors of this sort? Or is it a vertex that lives, I don't know, here maybe, and sees something different? So we need to sample a notion of type for this vertex. And let's say I did some random sampling for you. It gave me 0.34 for some reason. And now the next bit about this branching process is we need to specify how do we, as with most branching processes, how do you generate the children, the family tree. And so the idea here sort of is with this lambda from before, with the fairly simple Galton-Watson branching process, the lambda basically reflected the expected number of children that the vertex should have. And so what we need to do now is to find a corresponding idea of what it means to have a certain degree for a vertex. And so thankfully we are able to define the notion of a degree for in a kernel. So using this whole intuition of the graphon being some very, the adjacency matrix of a very large graph, you can sort of think of the way you find the degree of a vertex is that you add up all the zeros and ones along a column or row. Or in this case, because we are working with a function, we integrate from 0 to 1. And so by computing this degree, we have now established that we should generate Poisson so many children. But we sort of have another complication, which is that since we kind of care a bit more about where the vertices sit, we need to somehow assign them types as well. So we have something which I won't really get into details today, because it's a bit complicated. But the way we generate these children is according to a Poisson point process on the interval, which has some densities. Sort of the idea here is if I have more neighbors of a certain type, I expect more neighbors of a certain type of high intensity, then my children should be of those types and not some other type where I have very low intensity. Right, and so with that, maybe you ran this Poisson point process for this vertex 0.34, and it generated for you 3 children, and in these different places. So you get now 3 children of 3 different types. Maybe they come out with these numbers. So you now mark them on the unit interval where they sit. And to continue generating children, you sort of repeat the same process. You look at what their sort of neighborhood or degree looks like, and sort of generate more and more children. So this is just one example of where you might put random points for, let's say, this vertex marked 0.64. And, oh, already this. And sort of after you generate all these children, all these types, the one little thing I should mention here is actually, for the purpose of the branching process, you will actually forget the types and you will only look at the tree without these labels.
Going back to the random graph process here. What happens if wxy is greater than 1?
Right, so
is it
I didn't.
So
So
you're
you normally
sampling-
just.
you're dividing by n, but then
Yeah.
also you're multiplying by n because it's w over n in the second. So I'm looking at gn kernel divided
Right.
by normalized by n.
Yeah. So right. So what I didn't. Okay, I wasn't maybe too precise here. You should actually add a sort of, instead of writing this, it should be more like min this of a min of this and 1. Yeah.
Okay.
Actually, you want to only consider when n is very large. So this is for the sparse setting, right? These corner things, rather than.
W could be 없나?
Well, so this
we divide
model.
by this n.
Yeah, so this model is meant to consider when your average densities are some constant number, whereas n could be very, very large.
Okay. Yeah, I see how that. So you're really kind of normalizing by n squared because you first divide by n.
Huh?
Like if you have w is some kernel where you're integrating over a line to find the average degree, then if you look at if you just choose I and j randomly and look at some random edge, the probability that edge is there is you're dividing by n first there and then there, so you divide by n squared.
Sorry, I didn't understand.
So I'm just trying to.
So you have this kernel, and then
Yeah, just fix the
you have
kernel,
this. Okay.
and now look at the graph process gn
Right.
kernel divided by n.
Okay.
So there's 1 divided by n.
Yes.
And now what's the probability that ij is there? Is that just divided by n once or divided by n twice? 'Cause
No,
you
no,
say
you divide only
Since
once.
it's just notation W over n, then still probability is
It's
W
the
over n.
same.
Yes.
Okay. Alright. Sorry about that.
Yeah, sorry, maybe I should. So one thing is, normally people talk about GNW, but for the purpose of this model, we have this over n
Uh-huh.
because of
So you can write GNW and then the probability is W, right?
well, no, because the model they actually consider they have the divide over n in there. It's not actually a kernel always.
Okay.
Oh, I mean, okay. So the reason I didn't write it that way is because there is a model where the input in the second parameter is actually a kernel, and there they don't have to divide over n here as well.
Uh-huh. Yeah.
Okay. Sorry about that. I understand that.
Right. Right, so in summary, you have a branching process where you generate the first vertex, but you'd have to give it a type, and sort of you do something that's like the Galton-Watson branching processes from before, except you now have to basically care a lot about types of vertices. And sort of the punchline here, and which is one of the results of Bollobás, Janson and Riordan, among all the results that in this giant paper, is that if I am able to establish what the survival probability is for this Galton-Watson branching process of inhomogeneous types, then in fact the size of the largest component in this random graph is asymptotically what you get by taking the survival probability and multiplying by n.
Then do you know the condition when SW is non-zero?
It's a bit complicated because now that you are working with these kernels, you actually start working with an operator. And broadly speaking, it mirrors the original Erdős-Rényi result in the sense that when things are less or equal to 1, where you take some norm, which is a bit complicated, which is sort of corresponding to this less than 1 that you saw before, then it dies out and therefore it's small, and if it's greater than 1, then again you have this giant component. But the operator thing is a bit more complicated than I wanted to get into. Yeah. Right, and okay, so just to maybe give you a concrete sense of what these Galton-Watson branching processes might look like, let us look at the following 4 kernels. So here we have the first one being a constant 2 kernel, being the value is 2 everywhere, second of these 0.7 everywhere. The third of these is a bit more complicated, so we sort of the thing about it is you take the unit interval, you divide it into 2 parts, and sort of in the square I shall put zeros here as well, all zeros, and in this square I put 1.4, and here also 1.4. And sort of abstractly this corresponds to a balanced bipartite graph with density 1.4, whatever this might even mean. And here we have a different kernel where the partition is sort of unbalanced. So instead of half-half, we have, let's say, a quarter, 3/4 here as well. And we put sort of a value of 2 on the cross bits. So this again corresponds in a somewhat abstract sense to a bipartite graph with density 2, whatever this might even mean. And sort of, okay, so what might be Galton-Watson branching processes for these kernels be? So sort of recall the main difference between this inhomogeneous version of the branching process and the previous one that we saw earlier is sort of that we have all these types which added more complexity to our life. But on the other hand, sort of if you look at the first 2, for example, you looked at what the slices are, so what you get by taking the functions sort of like this and so on, then actually all of the points in this interval sort of have the same slice. So they're all 2s everywhere, no matter where you picked. And here also you have the same slices 0.7 everywhere, no matter where you looked. So what you actually get when you evaluate this Galton-Watson branching process is that this is simply just the Galton-Watson branching processes with parameters 2 and 0.7 that we got from before, because the types in some sense don't matter. All right, so now on to the third one. So you might at first glance think, well, this is somehow more complicated. There are bits where you see 0, you see 1.4, and you have this sort of partition in the 2. But sort of if you look closely and sort of recall a little what really mattered in the generation, what really mattered here is you had some types. And where the types came into the picture is that you had some generation where you looked at the degrees. So if you were to actually look at the degrees of each type, so each point in the interval 0, 1, you really just have 0.7, because if you integrate here, you see zeros for the first half and then 1.4s in the second half. And for things here, you also see again 1.4s, but then zeros. So in sort of both cases, you have a type of degree 0.7. So actually, it turns out to be exactly the same. So Galton-Watson 0.7. And so what about this last one? So you might think, okay, this is now genuinely more complicated because, well, not only are the sort of parts no longer sort of balanced, so now you have 2 parts of different sizes, but actually the degrees themselves are different, right? So you can sort of see, if you integrate here, you get a larger value than if you did an integral sort of this way. And so the sort of, so indeed you do get something a bit more complicated, and so it looks like this, which sort of the main sort of thing is sort of, instead of a simple single Galton-Watson branching with a single parameter 2 here, or some constant, now you have something which is sort of a quarter coming from when you take things in the first part, and 3/4 coming from when you sample things in the second part. And sort of when you sample things in the first part, then what you start off having is you have something of degree 1.5 because you integrate this value 2 over just 3/4, whereas the rest is 0. But then when you do the sampling, you sort of your children will necessarily be in the other part of the sort of this bipartition, so you sort of alternate between the two. And sort of similarly here, you also have this alternating thing where you sort of go between this part and the smaller part. So you get something like this.
In the notation, why do you put O is equal to 0.5?
Oh, it's just a random thing to denote that, like, in the first part you get, I guess, okay, so I had some slightly odd numbers where I started from generation 0. So in the even generations, you are here, and the odd generations, you are here.
I understand.
Yeah. Interesting. Yeah, sorry, it's a bit confusing because I made a slightly weird choice for this. Okay, and right, so after going through that, we are now sort of in a position to state sort of our main theorem, or at least half our main theorem. So what we are able to say here is that is to give a characterization of these Galton-Watson, inhomogeneous Galton-Watson branching processes, and say that if we have two kernels, U and W, then these two kernels generate the same process with the same distribution precisely when these two kernels have a certain property which is called fractional isomorphism, which I haven't yet actually introduced, and this will sort of come up right after this. Right, so now what I'll do is I will try to give you a sense of what this property of fractional isomorphism is. But to do this, I will start off by talking about what this is for graphs, and then say a little bit at the end about how this transfers over to these graphons or kernels. Right. So to begin, fractional isomorphism for graphs is a classical property. It's been studied quite a lot in the area, and sort of the motivation for this is that it's a relaxation of the usual notion of isomorphism in graphs. So in particular, it has some applications in sort of some decision problems related to graph isomorphism. And so what I'll start by doing is I'll give you one definition for this notion of fractional isomorphism in graphs. And in particular, to sort of mirror a bit what we saw before, I'll give one in terms of something called the color refinement algorithm. And sort of work to sort of say that this is a good definition. It was done by the following people, so Tinhofer and Ramana, Scheinemann, and Ullman. Right, so what is this algorithm? Disconnect. So it's the color refinement algorithm for a graph, not necessarily connected. So what we start off with is you start off with a dummy trivial coloring of all your vertices. So let me start by coloring every vertex V in the graph with some random element I picked. So let's say the star or something like this. It's just a choice that doesn't, yeah. And so what I'll do is, the way I'll refine my coloring is as follows. So this thing basically proceeds in rounds. And in each round, what I do to extend the coloring is that I take the current coloring of my vertex and I append to it a multiset of the colors of all its neighbors. Right. And so I sort of keep doing this refinement of the coloring by looking at adding this multiset of colors of its neighbors until I find that the two consecutive colorings have exactly the same color classes. And then the output of my algorithm will simply be the colors of the vertices. Right? Is everyone on board with this? Right, and so just to give you a example of this color refinement algorithm with a slightly stripped down example. So let's suppose I have a graph which has 3 vertex parts of equal sizes. So I represent these by these circles. And I have the following distribution of edges. So for vertices in the first part, each of them has degree 2 inside this vertex part. For a degree 4 going into the second part, and no edges going at all into the third part. And then for the second part, vertices in here have degree 0 inside this part, 4 going into here, and 6 going into this part. As for the final vertex set, it has 0 here, 0 to the first part, and 6 going into here for each vertex. Now, if I were to run the color refinement algorithm, what would I get? So, so in the beginning, vertices in each part have the same coloring. So if I'm a vertex in this part, I have color star. I'm a vertex in this part, I also have color star. And if I'm a vertex in this part, I also have color star. All right, so now let me refine my coloring. So let's say we look at a vertex in here. It has, well, its first part of the coloring is star. And let me refine its coloring. So what do? I append a multiset of the colors of its neighbors. So in particular, I will append a multiset containing 6 stars, because there's 2 neighbors in here and 4 here. Sort of similarly for this, I will append a multiset of 6 stars, because it has 6 neighbors here and nowhere else. And for the vertices in here, I put a multiset of 10 stars, because I have 4 here, 6 neighbors here, and none in here. Right, so sort of using this, we're able to refine the coloring. And then if I were to run this refinement one more time, then let's say I'm a vertex here. I have 2 neighbors in here, which have a coloring that essentially says that I have 6 neighbors, because that's all I know up to now. And 4 neighbors of degree 10, because again, that's what the refinement told me. So in some sense, I refine the coloring further with a tuple that tells me essentially I have 2 and 4. As for things in here, they have neighbors, 6 neighbors of degree 6, sorry, 10 neighbors of degree 6, 4 here and 4 here, and none of degree 10. Oh, sorry. And finally, vertices in here have 6 neighbors of degree 10 and no neighbors of degree 6. So I can sort of further refine the coloring with a tuple like this. And so at this point, because it gets more and more complicated to actually define the next step of this, I will sort of just jump to the end to say that it turns out that the next round doesn't actually give me more information. And so I stop here and output this as my final coloring. Sort of taking sort of the cut like this. Sort of. Okay, so with this we can give sort of definitions of fractional isomorphism. So the first of these definitions is, as I sort of went through before, that the color refinement algorithm turns out to give the same output of the colorings. And it turns out actually, through work of many other authors, that there are quite a few equivalent definitions, including 2 of which I have put here as well. So first of these says that 2 graphs are fractionally isomorphic if they have the same homomorphic counts of each fixed tree. And another definition of this is that 2 graphs are fractionally isomorphic if I can find a doubly stochastic matrix, so meaning that all the rows sum to 1 and all the columns sum to 1, such that such an equation holds with AH meaning the adjacency matrix of the graph H. Sort of to give you a sense of where this definition comes from, if you were to have a matrix which is not doubly stochastic, but rather a permutation matrix, P, for example, then the equation here with P instead of S, it simply sort of tells you that you will permute the vertices of G to get that in H. Right, and sort of to cap this off, in recent work by Grebík and Rocha, they were able to generalize all these three definitions and give equivalent definitions for graphons, and also show that the corresponding definitions for graphons turn out to also be equivalent. Right, and so in the final 10 minutes or so, I will try to give you a speed run of this last bit of my talk. So that sort of concludes the bit about these inhomogeneous random graphs. Now, we also looked at a result, or we also looked at sort of uniform spanning trees. So to quickly give you a definition of uniform spanning trees for a connected graph. So we say that the uniform spanning tree of a connected graph G is denoted by USTG, and this is simply, it's not a tree, but rather a uniform distribution on the set of all spanning trees of the graph G. And so here, unlike before, the word connected actually matters because it doesn't really make sense to talk about spanning trees when you don't have a connected graph. Right, and sort of, I won't get too much into the details of the entire theory, but just to give you a sense of how one studies these objects called uniform spanning trees. So there are well-known algorithms in the theory known as Wilson's algorithm and Alder-Sproeder algorithm that allows you to actually generate these things well and actually use these to study. And the study of uniform spanning trees has a lot of connections to the theory of electrical networks on graphs. And sort of...
So is this electronic network means that some weighted on the edges, or what one?
So you basically have a graph, you put what is effectively a resistance of 1 on each edge between two vertices, and you can talk about resistance between different edges and how you can, a theory that arises from this for behavior. So you can talk about things like what is the average effective resistance and many of these different things. And he has very close connections to the study of the uniform spanning tree. Right, and so one classical result, which has a branching process involved in it, is the following result of Colchin and Grimet from 40 odd years ago now, almost 50, that says the following: if I look at the uniform spanning tree of the complete graph Kn on n vertices, and I look at a sequence of graphs, which is basically Kn going to infinity, then the uniform spanning tree, if I looked at it sort of rooted at this vertex, at vertex 1, which doesn't really matter for Kn because it's symmetric, then this turns out to converge in a sense to a branching process, which I will denote by this, which basically is the Galton-Watson branching process with parameter 1 conditioned on the null set event that the process survives, because recall that this is, and just to give you a sense of how this looks like a one-way infinite path rooted at this vertex like this, with a whole bunch of Galton-Watson branching processes hanging off each of them with parameter 1. Right, and so when one studies things with graphons, the natural question to consider is sort of the following. Since this previous result of Colchin and Grimet was basically studying what happens when I have a sequence of graphs, Kn, converging to a graphon W, which is just the all ones graphon, what can we say about things in general? So a result of Harki, Nachmias, and Tran from 5-6 years ago now sort of gives an answer to this for a large family of graphons and says the following. If I now have a sequence of graphs which are connected, not necessarily complete, which have the property that they converge to a graphon W, and I have a slightly stronger condition than connectedness known as positive minimum degree, then it turns out that if I were to look at the UST, the uniform spanning tree of these graphs, now around a uniformly random vertex, because things are no longer so symmetric all the time, then it turns out that this has a limit, and its limit is something which we will denote by which we'll call the uniform spanning tree of the graphon W. Right, and so there is a whole definition for this, but just to give you a sense of what this object looks like. So if I were to have a concrete example here, so let's suppose I have this bipartite graph sequence converging to this graphon over here, and this has positive minimum degree because, well, you can sort of imagine that these are sort of complete bipartite graphs and everything always has positive minimum degree and it survives into the limit. Then it turns out, if you were to do the right computations, and sorry, so one thing is you can sort of see that this thing has sort of an alternating structure where you sort of have two parts, and things, when you do these branching things, like in all likelihood the trees will bounce back and forth. And it turns out that if you were to compute the uniform spanning tree for this graphon, you also have this bipartite behavior. So about a quarter of the time it looks something like this, 3/4 of the time it looks something like this. And the branching processes involved here also somehow alternate. So I won't really define what these are because these get a bit more complicated than what we have seen before. But it has the following form, where I haven't quite said to you what these GWABs actually are. And our main result in this direction is that we give a characterization of these uniform spanning trees for graphons. And we say that if you have two connected graphons, uniform minimum degrees, then the uniform spanning trees have the same distribution precisely when these two graphons are fractionally isomorphic, but not only then, in fact, as long as they are fractionally isomorphic, up to a constant. And so just to give you a sense of why this last extra complication might come in, now suppose I have two graphons, let's say the all1, which basically means the complete graphs, and the all constant 0.7s, corresponding to random graphs of density 0.7. Now, when I'm taking these uniform spanning trees, I'm really always taking a very, very, very sparse collection of vertices, a very, very sparse subgraph. And in some sense, no matter whether I pick the uniform spanning tree here for a graph that looks like this or for a graph that looks like this, in some sense, because the edges are somehow distributed fairly evenly everywhere, they turn out to actually look basically the same. And with that, which turns out to be this Galton-Watson branching process conditioned on survival. Right, and so with that, I'm at the end of my talk. Thank you for listening.
Thank you. Any questions?
I guess.
So in the Ehrlich-Renyi graph, is it similar to the branching process, and it's like you traverse the vertices in a BFS manner, isn't that? But is it the same if we traverse the vertices in any order? So we pick one vertex and we branch. We look all the children's and not in BFS order, but we choose any vertex and then also do the same.
Right. So I think the point is. You might not get, you will more or less get the same. Oh, sorry. Right. So the point basically is that one thing I didn't mention in this is that, and this is something that actually comes out of the theory, is that basically in this regime, things are more or less tree-like. So of course, this more or less is somehow carrying a lot of weight. So a lot of the details. But more or less, if you were to try to do things in a different order, you won't really see different things. So I guess the short answer is it doesn't really matter. But of course, the exact tree might look different in an actual realization of this tree.
Thank you.
I didn't quite understand what is a uniform spanning tree around the vertex. Like the process is starting from a vertex and building out, but it doesn't. The tree you're getting does seem to depend on the vertex you start with. Maybe not.
Right. Wait, sorry. There was
A uniform spanning tree probably shouldn't depend on the vertex that you start from, right? I mean, a uniform spanning tree is
right. So
contains all the
for the
vertices.
uniform spanning tree, that's simply just one of the
uniform spanning
Yeah.
tree. Yeah. But
One
then
of the spanning tree chosen
you choose it randomly at random.
Yeah. But then was there something about? But then the process does build from a particular vertex, and you're saying conditioned on you've got this process with parameter 1 and conditioned on it. Yeah, this is the diagram I'm thinking about.
Yes.
So where is it says around?
Right. So
Yeah, what is the meaning of around vertex 1?
That's the question.
Around a single vertex.
so
it's
okay,
always
so-
like a tree
so-
star.
so what I mean by this is sort of you have all the spanning trees of Kn, and the usual uniform spanning tree is that you pick one of these. You essentially have a uniform distribution on the spanning trees. What I mean by this around vertex 1 is sort of this is probably something that is a bit of an artifact from the result, but rather if you focus on the structure around this vertex, then sort of you can think of it as having a root somewhere, and it will look like what you see starting from this rooted at this vertex.
Yeah, but then this doesn't look symmetric because there's this this long one-way path with kind of smaller trees. So it seems like now that is the tree depending on the vertex 1 that you get.
Well, it's
Because you've got
so
one.
maybe the way I'm drawing this makes it look asymmetric, but like if you sort of
But because of the GW1 or
so
something.
so the point is you don't necessarily know where this branch will be, right? So the point is like sorry, I didn't quite understand your. So
Yes.
like there is
where does 1 live in this drawing, for example? You says
Where does
around vertex 1,
live
and then you
in-
have this process where you are building a rooted tree, but then because it's conditioned on the tree surviving,
right.
Then it the way that I see this picture, vertex 1 is over on the left of this.
Top left.
The top left
Right,
of this
so-
picture. But then now it doesn't. Now I can tell which vertex is vertex 1.
Right. I understand what you're asking, but let me think about how I want to. So sort of the point is, it's not so much about 1, but rather I want to say, let me look at what the trees would look like if I were to stand at 1 vertex. It's not, so I'm not necessarily giving a label. So the point is, if I change this to, so the point is at vertex 1, so what I mean is I'm looking at the neighborhood structure coming out of 1. But if I were to change this to whatever number you want,
Then it should be
1,000,
the
whatever,
same.
that would be
Also
the
the
vertex
same.
here. Yeah. So it's not so much that I'm giving the vertices labels that sort of then change depending on where I look. If you got it.
I think each GW1 is always distinct.
Right,
distinction
they all
and
look different.
choice of this, and only the one way survives. We only condition this, so after we choose this, and still we can understand this is lies of the first GW1.
Maybe there were more just now. Maybe some had a question.
So if I remember correctly, then UST concept and electric network concept highly related to eigenvalue in the graph case. Then is there also somehow eigenvalue characterization or some relation of the spectrum and this fractional isomorphism concept?
So I unfortunately don't know too much about this side of the theory, and I can't really say. I'm not aware of anything. But
So maybe I have some related question, but very light. So is there any relation between the relation to the matrix tree theorem? So
the what, sorry?
matrix tree theorem. So just counting the number of the matrix using the Laplacian matrix, or is there any?
Matrix
I'm not-
or counting spanning trees. right?
Yes, yes, yes.
I'm not aware, but I'm also not too familiar with that side.
So could I see the last thing? No,
Actually.
I just want to. So you just, I mean, in the case of this bipartite graph with the 0, 1.4, 1.4, 0,
Mhm.
it gives the same value of this it's the surviving properties was same, right? With
You mean-
this.
Well, in the Galton-Watson setting, not in this setting.
Okay, in this setting different, right?
The setting is very different.
Ah, okay.
So when two graphons are fractionally isomorphic,
Yeah.
is this the? I mean, are there other properties known? I mean, it seems
So
very strong, right? That you can find a doubly stochastic matrix to
Yeah.
commute, and yet
well,
spanning trees already describe the fractional isomorphism, so it's
right. So to my knowledge, there isn't too much known about fractional isomorphism for graphons. So really, this work was done like 2 years ago, and yeah.
Can you go to the part where you give examples on the branching process for kernels? I remember there were 4. Yeah, this one. So you said GW. The third one is exactly same as GW 0.7, but
Yes.
it seems to. I have a feeling that it has to be contain some bipartite structure, but it's just.
Right. So the thing that we don't see because of how you do this is that you will, when you generate a tree, in theory, you keep track of the types, then you will see the structure. But the way that the process works is that we chuck away all the types at the end. So then at that point you just don't see the structure anymore. So because you only really have a tree, which you cannot really use to determine whether there's bipartite structure.
so these two, the second one, the third one, are fractionally isomorphic.
Yes.
So you have a. I see. So you can multiply some.
Yeah, so in particular, one thing you get from these things is that all regular graphs are fractional isomorphic, for example.
All right. Any more questions? If not, let's.